So up to this point, we've been able to determine a solubility product for a particular reaction, that's its KSP value, or we've been able to determine the molar solubility of a salt. So how much of it will dissolve in a liter of solution. So the next topic we're going to discuss is predicting precipitation. Can we determine whether or not a salt will precipitate out of solution or remain in solution if we know its reaction quotient? So the KSP values are going to be compared to these reaction quotients, and we discussed reaction quotients back in chapter 13. They were represented by that value of Q. And they're solved the same exact way as the KSP. They're products over reactants, each raised to their respective coefficient. The only difference is Q means that we haven't quite reached equilibrium yet, so we're still in the process of getting there. And we can use these two values to determine whether or not a salt will precipitate out or stay in solution. So my KSP is going to be my barometer. It's my bar. And it's going to be provided for me in all of these problems. And if my Q equals my KSP, I've reached equilibrium. If my Q is less than my KSP, the solid will continue to dissolve until my Q value equals KSP. So if my Q is less than my KSP, I'm going to have no salt formation whatsoever. Everything is going to be dissolved in solution. If my Q is greater than my KSP, precipitation will occur at a given temperature. So we'll start to see something crash out of solution. So for the following reaction, we have calcium carbonate, and it's going to break into its two respective ions, calcium and carbonate. We can establish this equilibrium either by adding solid calcium carbonate to water or by mixing a solution that contains calcium and carbonate ions. And then we can compare the numerical values of my Q and the theoretically provided KSP value to predict whether precipitation will occur. So let's take a look at a problem where we're going to actually try and predict whether precipitation will occur. So here we go. So the first step in the preparation of magnesium metal is the precipitation of magnesium hydroxide from seawater by the addition of lime, also known as calcium hydroxide, a readily available, inexpensive source of the hydroxide ion. So in my seawater, I have magnesium 2+ ions, and to it, I'm going to add my calcium hydroxide to be my hydroxide source. So my calcium is simply just a spectator ion, so you can ignore it in these problems. My overarching ionic equation is the magnesium hydroxide solid that I want to precipitate out of solution is going to break down to form magnesium 2+ and 2 hydroxide ions. So for every 1 magnesium, I have 2 hydroxides. And its respective KSP is 8.9 times 10 to the negative 12. The concentration of magnesium 2+ in seawater is 0.0537 molar. Will the magnesium hydroxide precipitate when enough calcium hydroxide is added to give a hydroxide ion concentration of 0.001? So there's a lot going on there. So the first thing we want to do is we have our ionic equation. So let's write our KSP expression. So on the next slide, I have my solving of this. And instead of a KSP expression, I'm going to write a Q expression, a reaction quotient, because I'm provided the KSP, and I want to see, am I at the point where I've reached my KSP? So here I find that my Q is equal to my magnesium concentration times my hydroxide concentration squared. So Q is solved the exact same way as my KSP, we just haven't reached equilibrium yet. So if that's the case, I know my magnesium ion concentration is 0.0537. It's provided in the problem. So I can plug that in for that value. My hydroxide ion concentration is 0.001 molar. That's provided in the problem. So I can plug that in as well. And I'm going to square that value simply because I have 2 hydroxide ions for every 1 magnesium. So I'm going to have to square that value because that is a coefficient of 2. When I solve for this, I find that my Q value is 5.37 times 10 to the negative 8 mole, or 10 to the negative 8. There's no units, it's a reaction quotient. So the next thing I can do to determine will this precipitate or not is I'm going to compare my Q value to my KSP value. What I find is my KSP is less than my Q value. And what that means is that magnesium hydroxide will precipitate. It will crash out of solution. I'll be able to basically abstract all of that magnesium that I'm looking to take from seawater. So if my KSP is less than my Q, I will see precipitation form. So let's try another one. Use the solubility product, 7 times 10 to the negative 7, to determine whether calcium biphosphate will precipitate from a solution with a calcium ion concentration of 0.0001 molar and my biphosphate concentration of 0.001 molar. So if I'm looking to see if something will precipitate, I know that I have to find a reaction quotient to compare to my KSP. So let's write up an ionic equation as well as a Q or reaction quotient expression. So here what I'll find is, in this particular case, my ionic equation, which I don't have written here, but it's going to basically break into two components. I'd have solid calcium biphosphate, and it would break into the calcium 2 plus ion plus the biphosphate 2 minus ion in a 1-to-1 ratio. So I could write my reaction quotient expression of Q equals the concentration of my calcium times the concentration of my biphosphate. I know the concentration of both because they are provided in my problem. So for my calcium, it is 0.0001, and for my biphosphate, it is 0.001. So I can multiply those two values, and I find that the reaction quotient is 1 times 10 to the negative 7. Once I know that, I can compare it back to my KSP expression, and I find that my KSP is larger than my Q. So therefore, I have not reached my maximum amount of ions dissolved in solution, and therefore my calcium biphosphate will not precipitate in this particular case. I can add more calcium biphosphate, and it will still dissolve in solution. Let's look at another one. Precipitation of silver chloride upon mixing solutions. So does silver chloride precipitate when equal volumes of a 2 times 10 to the negative 4 molar solution of silver nitrate and a 2 times 10 to the negative 4 molar solution of sodium chloride are mixed? And it tells me that KSP is 1.6 times 10 to the negative 10. The solution also contains sodium and nitrate ions, but when referring to solubility rules, one can see that sodium nitrate is very soluble and cannot form a precipitate. So let's solve this. So we're going to do the same thing that we did in my previous two problems. I'm going to write an ionic equation. So my silver chloride is going to break down into the silver ion and the chloride ion, because the salt that's really being formed is silver chloride. My sodium nitrate is a soluble salt. It'll stay in solution. So my reaction quotient says that it is equal to the concentration of my silver ion times my chloride ion, and I have to find their concentrations in the problem. It tells me that the concentration of my silver nitrate is 2 times 10 to the negative 4 molar. That's just for my silver ion. And for my sodium chloride or my chloride ion, it's also 2 times 10 to the negative 4 molar. What I'm going to do is I'm going to divide each of those values in half. The reason why is because if I'm adding equal volumes, I'm going to actually dilute these samples. So I'm going to change their volume. I'm going to double their volume. And what that ended up doing is halving their concentration. If you remember your M1 V1 equals M2 V2 days of Chem 151. So the concentration of my silver ion is actually 1 times 10 to the negative 4. And the concentration of my chloride ion is also 1 times 10 to the negative 4, since I've diluted those samples upon mixing. Once I multiply those two values, I find that my reaction quotient is 1 times 10 to the negative 8, and I can compare it to my KSP. My KSP is less than my Q value, therefore my silver chloride will precipitate out. So in this particular case, once I've added these two solutions, I'm going to find silver chloride as a white solid precipitating out of my solution because I've reached the capacity of how much silver chloride can dissolve in my solution. So this next problem is going to look very similar to the one we've seen before. Will potassium perchlorate precipitate when 20 milliliters of a 0.05 molar solution of potassium ions is added to 80 milliliters of a 0.5 molar solution of perchlorate ions? Remember to calculate the new concentration of each ion after mixing the solutions before plugging into the reaction quotient expression. The KSP is 1.05 times 10 to the negative 2. So what I want you to do is I want you to pause this right now, and I want you to attempt to solve this using what we did in the previous problem, and then come back to the video and I will solve it as well. So in this particular problem, I'm going to look at my potassium ion first. So my potassium said I had 20 milliliters of a 0.05 molar solution. So I'm going to multiply that concentration, 0.05 molar, by its volume in liters, 0.02, to find out how many moles I had. I had 0.001 moles of the potassium ion. I'm then going to divide it by the total volume of the solution, because remember, I'm mixing two things. I'm mixing my potassium and my perchlorate solutions. So my total volume is 20 plus 18, so 100 milliliters. So I'm going to divide my moles of potassium by 0.1 liters, the total volume in liters. And I find that the new concentration of potassium ion is 0.01 molar. I'm going to do the same exact thing for my perchlorate. For my perchlorate, I have 0.08 liters. That comes from my 80 milliliters. I'm going to multiply it by 0.5 molar, its respective concentration, to find that I have 0.04 moles of my perchlorate ion. I'm going to divide that by the total volume as well. So 0.1 liters gets me a concentration of the perchlorate in my new mixed solution of 0.4 molar. Now I can take my reaction quotient expression. So my reaction quotient is equal to K plus times my ClO4 minus. And this isn't a one-to-one reaction, so if you want to write out your ionic equation, that might be helpful in putting that together. And I can plug in the concentrations that I solved for. So for my potassium, it's 0.01 molar. For my perchlorate, it's 0.4 molar. Multiply those two values, and I find my reaction quotient to be 4.0 times 10 to the negative 3. I see that my KSP is greater than my Q value. The KSP for this particular substance is 1.05 times 10 to the negative 2, so it's been given to me. Since my KSP is greater than my Q, the potassium perchlorate will not precipitate out of solution, so it will remain in solution. No solid will crash out. So that is how we can solve for whether or not I take two solutions and mix them and see will something precipitate out or not.